Okay, so our first section in this unit is slope of the tangent line. So this is one of the big problems in calculus. There's two main problems. One is the slope of the tangent line, the other one is the area under the curve, and we won't get to the area under the curve until second semester. So we're going to spend a lot of time on slope of tangent line. No, not really, but sort of. The goal of the goal of the problem is to find the slope of the tangent line. So why is that difficult? Well, if you think about what a tangent line is, it's a line that touches the function at a single point. So if, there we go. So if we have a function, maybe we have a point right here, and the tangent line would look something like this. Okay, it doesn't mean it will never cross the function elsewhere, because if we extend that line, it will in fact cross the function. But in that region around that point, that is the only place that it crosses the function or touches the function. So it essentially touches the function at one point and kind of follows the curvature of the function, maybe a little bit, I guess. So we're going to start the idea of this with estimating the slope of the tangent line. So how in the world are we going to estimate the slope of the tangent line? You can only find the slope with 2 points, and we only have 1 point. So how we're going to do that is we are going to find the slope of what are called secant lines. So secant lines are lines that go through 2 points on a graph. So we're going to pick a point somewhat close to 1. So maybe we could pick 1.5. All right, so it's not too far away. And the y value for that is 2.25. So how did I get the y value for that? 1.5, plug it into x squared. Our function is x squared. So my y value is going to be 1.5 squared. Sorry, I probably should have explained that before. I just wrote down 2.25. So we're going to find the slope using this point and 1, 1. So if we find that slope, we do y2 minus y1 over x2 minus x1. And if we calculate that, that ends up being 2.5. So that's the slope of our tangent line. So how good is that approximation? So I've got a little animation here. Well, it's not animating at the moment, but this is showing you y equals x squared in the red. And then the, I believe it's the green line is the actual tangent line. And then the blue line is our secant line going through 1.5. So this line is going through 1, 1, 1, 1 is B. And then this point is 1 point, at the moment, 1.5. I've set it to be 1.5, comma 1.5 squared. All right, so this is our estimated slope, and then this, the green line, is our tangent line slope. So as you can see, it's not bad, but it's not the greatest. And so what's going to happen as we pick, how could we make this better? So if we use this little slider to do different values for A, we can see that, if we make A larger, if we move that point further away from B, our secant line slope is going to get further away from the tangent line. But if we move that point closer to B, we can see that we're going to get it to be very, very close to the tangent line. All right, if it is B, it will be the tangent line, but that's because I'm just sliding it along the curve until it meets B. It's impossible to find the slope with just 1 point. But if we make that A be super close, I can only get it on the slider to within 0.1. I could type in a value for A and show you that. But anyway, you can see the slope of that blue line gets really close to the slope of that green line. So how we can make our estimate better is by picking a point closer to 1. So we get a better estimate by picking a point closer to 1. So let's pick 1.1. All right, so 1.1 is our x value. We want to plug that in to get a y value. So 1.1 squared is 1.21. So this is 1.1 squared. And then we can find our slope for that. So 1.21 y2 minus y1 over x2 minus x1 and that gives us a slope of 2.1. So we can see, you know, that's a little bit closer. We could get it even closer. We could do 1.01. We could do, let me go back to that Desmos thing. We could actually make A go on the other side of B and try to do those slopes. All right, so we could get it even closer. If we did, let me change A to be 1.01. We can see that on the graph, when we make A 1.01, they are almost exactly the same line. So we could keep progressing our point closer and closer to 1 until we were convinced as to what the slope should be. All right, this kind of looks like, we can even see just from these two estimates that is probably 2. We started at 2.5, we got to 2.1. If we did 1.01, we could get even closer. I don't want to because you kind of get the idea. So what are we doing with this? If you think about this, this should be somewhat familiar. All right, this is sort of what we did in the tables with limits. All right, we wanted to find the limit, say, at x as x goes to 1. So we would pick things like 1.1, 1.01, 1.001, and watch those y values get closer to a particular value. Well, here we're not watching y values get closer, we're watching the slope get closer to a particular value. So the slope of the tangent line is the limit of slope. Okay, so what we're going to do to find the actual slope of the tangent line is we're going to take the limit of slope. And to do that, we need 2 points. One of our points is going to be a generic point, a variable point. The other point is going to be 1, 1. Okay, so our variable point is going to be x, and our y coordinate for that point is going to be the function. It's going to be x squared. So with all of our points, how did we find the y value? We plugged the x value into our function. Well, if our x coordinate is x, then our y coordinate is x squared. All right, and we're going to set it up. We're going to take the limit as x goes to 1. All right, so x goes to our x value. It's this one that we're looking at, not the y value one. I know it's confusing because they're both ones. And we're going to set up slope. We're going to do y2 minus y1 over x2 minus x1. All right, and we want to solve that. And always, your limit is going to be 0 over 0. So if we plug in 1, we will get 0 over 0. So that means we need to do something, and in this case, we need to factor and cancel. All right, so that's why we studied limits, because we're going to use it to find the slope of the tangent line. All right, so we factor, we cancel, and then if we plug in 1, we get 1 plus 1, which is 2, which is what we thought it was. So instead of picking points progressively closer to 1, we can just jump right to the limit. You will not do this on your homework. You will do the limit. Okay, so you're going to try to find the slope of the tangent line to 3x squared at x equals negative 1. Now, I didn't give you the whole coordinate pair here, so let me help you set this up. If your x coordinate is negative 1, how do you figure out what your y coordinate is? You plug it into the function. So your y coordinate is going to be 3 times negative 1 squared, which is 3. All right, so you're going to do the slope with negative 1, 3. As your actual point, and then your other point is going to be x comma 3x squared, and then you're going to do the limit of slope. So you want to see if you can factor and cancel and get an answer for that. So going on, instantaneous velocity is the same thing. All right, so this is where we actually get into some applications. Those of you that have taken physics or are taking physics, there's a lot of physics applications with calculus. So instantaneous velocity is the same thing. Any instantaneous rate of change is the same as the slope of the tangent line, because remember that average velocity or average rate of change is slope. All right, so instantaneous velocity will be the limit of the average velocity or the limit of the slope as the 2 points get closer and closer together. All right, so if you want to find the velocity at any single point, you're going to do the exact same thing as finding the slope of the tangent line, because velocity is slope. It's your distance, change in distance over change in time. It's the same thing as slope, change in y over change in x. All right, so let's take a look at this one. If the distance function for a particle is s of t equals square root of t, the minus 1 is not inside the square root. I just didn't write that very well. Find the instantaneous velocity at t equals 9. So this is asking us to do the exact same thing as finding the finding the slope of the tangent line. All right, we want to find the velocity at a point. So how in the world do you find velocity at a point? Because usually when you find velocity, you need 2 points. You need a range, an interval, a time interval. But we don't have that. So how we're going to do that is we're going to do the limit of the change in position over the change in time. So we need 2 points. One of them will be a number. So t equals 9. So how do we find our y value? We plug 9 into our function. So we're going to get the square root of 9 minus 1, so that's 3 minus 1, or 2. And then our other point is going to be a generic point. It's going to be t comma the function, square root of t minus 1. So when we set up our limit, we're going to set up the limit the same way. We're going to do the limit as t goes to 9. So limit as your x goes to your x. We want our x values to get closer and closer together and see what happens to the slope. And then we're going to do slope. So we're going to do y minus y. And by the way, you could subtract them in the other order if you wanted to. I always just put the variable first, over x minus x. So then we want to simplify this a little bit. Hopefully foreshadowing, you can see that we're going to multiply by the conjugate because we have a square root in there. But before we do that, we want to simplify. So -1 minus 2 is 3. And we're going to go ahead and multiply by the conjugate to solve this limit. And when we multiply by the conjugate, remember you multiply firsts. So square root of t times square root of t is t. And lasts, we ignore the middle because they'll cancel. So -3 times +3 is -9, which is what we want. Otherwise, nothing cancels and we did something wrong. All right, so then we can cancel this. Oh, I forgot I was going to do this a different way. We'll do that on the next one. Actually, I'll illustrate on this one before we do the next one. Anyway, so we plug in 9. We're going to do the square root of 9 plus 3 equals 1/6. All right, square root of 9 is 3. 3 plus 3 is 6. So there's my slope. I forgot that I was going to do this a different way. There is another way to kind of set these up. And it involves setting it up slightly differently. So what you do when you set it up, instead of picking a generic point and having your set point, you have your set point and then you say, I'm going to go a little bit away from 9. All right, it's the same concept. You're picking another point on the graph a little bit away from the point that you have. All right, we had in our first example, we had 1, 1, and we picked 1.5. All right, so this 9 plus h here, this is our second point. All right, so 9 plus h and then f of 9 plus h is what this is. All right, we plug in the 9 plus h for t. So we're going to take our original point and we're just going to go a little bit away from it. The further away you go, the worse the approximation if you were not taking the limit of it. So this one, the function just happens to be flat enough that you can't see that it's really off. But here, the green line is the tangent line, and then this blue line is the secant line, and then the red is the actual function. So it just so happens that our function is flat enough that it's hard to see the difference unless h is gigantic. But as h gets closer and closer and closer to 0, we are going to get closer and closer to the tangent line. So I'll show you how to set that up in the next example. I'm going to go ahead and stop this video and do a second video on the other example.